in history of science and in the history of metrology. Without further ado, I'd like to call on stage Dr. Chenge Dimana from the DTI to give us the official opening and welcome to the Congress. Thank you.
Good morning, ladies and gentlemen. My role here is quite straightforward. I'm just here to welcome you all. I think maybe before I start with that, just to say that for those of you who were not here on Monday, my name is Chenge Dimana. We have changed gears from Monday to today. Today's conference is about the revision of the system of international units that we all know as the SI. It's no longer the 4IR that we had on Monday. So without further ado, let me welcome the distinguished guest, starting with Dr. Oswald Chinyamakovu, who hails from ARSO, from their head office in Ethiopia. Then we have Dr. Tim Pryor from the National Physical Laboratory. We have directors from AfriMets, which is the National Metrology Institutes in all the African states. And then we have colleagues from the University of Cape Town. And I take it we also have colleagues from the University of Pretoria. We have senior staff from the industry, the technology industry. We have, of course, the speakers that we will hear from today. I think, I think that's, with that, I can say that we declare the conference to be open. Thank you.
Thank you, Dr. Dimana, for that warm welcome. We move forward to the next part and the first presentation. The presentation is on the introduction to the revised SI. It is presented by Dr. Wynand Low. Dr. Wynand Low is our Director for International Liaison and Research. He is the current president of the CIPM. He is the first African president of the CIPM since establishment in the 1800s. We deliberately say African because we fully understand that his position is truly representative of Africa and not just for our country. And during his tenure, we hope to see many wonderful things coming from the CIPM to the benefit of African metrology. Let's welcome Dr. Wynand Low to the stage.
Colleagues, good morning. While Jayesh is getting my presentation onto the computer, it's really a pleasure to be here. It's nice to see all of you here. Dr. Dimana, that I know him for 25 years. He's not that old. 25 years, so it's really a pleasure to have you here today. Dr. Oswald Chinyamakovu, I took about 10 years before I could say his surname, but welcome Oswald, it's really a pleasure to have you here. Our CEO, Nwakulu Mukufi, and all the other distinguished guests. And it's not only you in the room, we also have an audience outside, and welcome to you as well. I've got a very nice job today because I don't need to technically tell you exactly what the revised SI is. Because after me, there are technical experts from the UK, from the Nmisa, also from our industry that will actually tell you exactly what has happened and what will happen. So I decided to make it a bit more lighthearted today, and I'm going to look at why do we actually need a revised international system of units. And I will show you that we have a system. And this system in the metrology world, and of course metrology is the science and application of measurement, is a universal measurement system based on sound scientific principles that can be applied universally. Of course, it must be effective. It must have the ability to properly calibrate measuring instruments with measurement uncertainties that are fit for purpose against an appropriate reference via national standards or certified reference materials, CRMs. And this system is called the International System of Units, and we will talk about that today. So what are the essential factors then? If you have this International System of Units, you must now establish effective metrology systems. And basically the first one is, of course, they must be traceable to this International System of Units that has been established. Or if we don't have a reference, an international reference for something, we can say we agree on what that reference will be. Then we went and we regulated measurements and measuring instruments. A good example will be speed measuring devices that all of you are familiar with. And then, of course, we must have confidence in testing and measurements results via certification, standardization, accreditation, and calibration. We call it the quality infrastructure, all of that together. So, of course, our measurements must be stable. It must have long-term trends that can be used for decision-making. If we measured something 50 years ago, we want to be able to measure it now and compare those two measurements. For that reason, it must be comparable. Also, if you do a measurement somewhere in the world, in a lab, you do that same measurement on the other side of the world, in another laboratory, you must be able to compare and bring together those measurements results. It must be coherent. So the results from different methods, you should be able to compare and bring that together as well. So there's the system. Why then a revision of the International System of Units? Earlier this week, in this room actually, we had a conference on metrology in Industry 4.0. So what must we do as metrologists to get ready for Industry 4.0? And I'm quite sure that all of you in this room know what we are talking about if we talk about Industry 4.0. But it is, of course, where man meets machine. I don't like to say man and woman, of course, meets machine and the digital thread, and we can throw around all these words. But I then, when I prepared the talk for Monday, had to research the measurement systems and if the measurement system is fit for purpose. And I went and I looked at the history of measurement and the history of the industrial revolutions. And something very interesting came up, and I'm going to show you what came up. So about 5,000 years ago in Egypt, Mesopotamia, the Indus Valley, there was a lot of development of measurement standards. And Jennifer Clark, that's talking after me, will tell you more about that, about the history of mass measurement, for example. But so that resulted in measurement systems like we had in Egypt, where we had the cubit as the measurement standard for length, about this long, and it was made of granite. And then they had working standards of wood. And once a month, they brought those wood standards, and they calibrated against that granite standard. I've actually got one in my office at work, very nice thing. In that way, they could build the pyramids very accurately. So that type of development of measurement systems continued until about 2,000 years ago, or arguably about 1,000 years ago. Then after that, in the period about the year 1000 to 1874, and I'll tell you later exactly why 1874, there was the development of systems, national measurement systems. And most of it was based basically on body parts. So you had in the UK a system that we call the imperial measurement system that was based on an inch, so this distance, and then a hand, and then a foot, and a yard also based on that. And then in 1875, we introduced something new, the meter convention or the metric system. And we're going to look a bit at the history of that very shortly. Not a long story. It is a long story. It took about 300 years to develop, but I'm only going to take about 5 minutes to tell you about it. So at that time, and I will show you now how it ties into the first industrial revolution, they created a decimal metric system. And that was done at the time of the French Revolution. Actually, the development started in the 1600s, and it went into the 1700s. And at the end of the 1700s, they officialized that system. And basically on 22 June 1799, there was a platinum standard made. That was the start of the metric system. And I'm not really going to talk about that. The talk after me will explain exactly what that is. But in 1874, they actually introduced the CGS system, and where the units were the centimeter, the gram, and the second. And you know that the whole meter convention or the metric system started with taking the Earth and say, okay, we want a measurement system that is based on the constants of the Earth. And they said, okay, we will define length in terms of the meter, and that is 1/10,000,000th of the distance from the North Pole to the equator. That is exactly what the meter is. You then divide it by 1,000, you get to a millimeter. 10 millimeters is a centimeter. And we then took a little block of water, 10 by 10 by 10 millimeters, and we said that is 1 milliliter, and that weighs 1 gram. That is where the kilogram comes from. 1,000 gram is 1 kilogram. We then said, okay, that's 1 liter. So there you have the kilogram, but Jennifer will tell you all about that. But so that was introduced in 1874 already, and then officialized in 1875. On 20 May 1875, 17 countries actually, signed the meter convention. And they agreed to, from that point, use the metric system as the universal measurement system. And so basically at that time, they introduced the meter, the kilogram, as I just explained, and another constant, the second. And of course, based on the rotation of the Earth, the length of a day and night divided by so many thousand gives you 1 second. So in the years that followed, in the 1900s, this system was further improved. And they added the ampere for current, of course, the Kelvin for temperature, and we have 2 of our colleagues that will talk about that later, and the candela as base units. And then later in the 1970s, they added the mole for amount of substance. And that created the international system of units with its 7 base units. We call it in French because this whole development of the metric system basically took place mostly in France. And the French then said, you can come and establish the International Bureau of Weights and Measures in 1875 in Paris. And so they called it Le Système International de Unité in French, the International System of Units. So there we had the system. Is it not fit for purpose? Let me show you what happens if you then look at the industrial revolutions. And the first industrial revolution is Industry 1.0. And it basically was mechanization. And they started to use water and steam power. Now, that happened in the 1700s. And if you now go and you have a look at what technologies were started then, and basically what measurements do you need? In the first place, of course, if you now use steam as a method of power, so you have a steam engine that can now drive something for manufacturing, you need to measure temperature. And it's very interesting that if you go, you will see that the development of the Celsius scale happened in the 1700s. Actually, Anders Celsius developed that scale and published it in 1742. So then they had a way of actually accurately telling people what the temperature is against a scale. And that scale, of course, was based on the freezing and the boiling point of water, as you know. The other thing that happened, and I got a slide from a colleague of ours, Pieter Greef, at the Nmisa, was that they started to manufacture things in components that you can then put together. That was part of the development in those years. And this is a sketch of a musket gun Most of you are too young to know what that is. But basically a musket gun that was a front loader gun. And this guy, Eli Whitney, started to manufacture that for the army, of course. And he got the contract to make 10,000 muskets in 2 years. They said he had no factory, he had no experience, but of course he knew somebody in Parliament. So and that's why he got the contract. And, but now you need some measurement technologies for that. So for that period, and think about when we said the metric system started in the 1700s, but for that period, 1700 to about 1860, 70, was the first industrial revolution. Those systems that each country had, the imperial system in the UK, the USA imperial system, based on the UK one but different, was fit for purpose because you manufactured something in your country, basically for your country. So you didn't need to make it comparable to something in another country. But now let's look at Industry 2.0 that then started after that. And that was basically from 1870 to early in the 1900s. And that was the time of mass production and assembly lines. So let's look at the technologies or the measurement technologies that you need for that. So suddenly you had this huge factory that you were producing 1,000 cars a day on this assembly line. I think that is the Model T Ford in that photograph. So you needed other things. In the first place, you needed electricity for the manufacturing process, but also for lighting. So you had to light up that factory because you actually want to work 24 hours, not only 12. So there was a lot of development at that time around electricity and measurement of electricity. Things like vacuum tubes. They started to find out that if you heat the filament, you can get a beam of electrons from it, and you can steer that with deflection plates. And so that was the start of television technology and so on. But all those developments actually took place at that time. So for Industry 2.0, 1870 to early in the 1900s, those type of measurement technologies and the measurement system was fit for purpose. And remember, that was still based on the constants of the Earth, circumference of the Earth, the rotation of the Earth, and so on. But then came Industry 3.0, and that is basically where the computer was introduced. Now, the first mechanical computers were built thousands of years ago. Already the telraam, we say in Afrikaans, I never know what the English for that is, but that was already developed in the Egyptian times. But real mechanical computers were built in the 1850s, 60s, 70s. There was a guy in Britain, Mr. Gabbage, and he actually built the first analytical machine or analytical computer, but that was a mechanical computer. But the first real programmable computer was built between 1936 and 1938 by a guy called Konrad Zuse. And he built it in his parents' living room. If you look at the size of that computer, it was a big living room, luckily, but it was a huge thing. Of course, still based on valve and tube technologies. Now, of course, most of you are too young to know what a valve and a tube is. I think Eddie still knows, at least. But that was then the start of microelectronics as we know it today. And from that big computer, they then started to miniaturize computers up to where we have our laptops on the desks, quite a few of them standing here today. And of course, you even have a computer inside your phone. And that computer inside your phone, the size of 1 by 1 centimeter max, is 1 million times more powerful than that first big computer in that living room. But now, what technologies do you need? If you start to talk about microelectronics, semiconductors, it's silicon technology, that's where it started. But then you had to basically make epitaxial silicon layers on silicon or other semiconductor materials like aluminum, gallium arsenide, and so on. And you had to be able to basically measure thin layers of a few micron. So 10 to the minus 6 meters, very thin layers. Then suddenly you need very powerful microscopes to actually see those thin layers. And they found that optical light was not good enough anymore. So they needed something with a shorter wavelength, higher frequency, and then they went the way of scanning electron microscopes. That is a photograph of our newest scanning electron microscope at Nmisa. It cost us about 20 million rand. For our visitors, that's about 1.2, 1.3 million euro or dollar. And X-ray photoelectron spectroscopes that could see monolayers on a surface, that's our XPS at Nmisa, another 20 million rand. And you needed technology to really be able to see atoms. And that's actually a photograph of a copper grid. And on the right-hand side there, the little dots are actually individual atoms. When I was at school, we basically said, we will never be able to see an atom. We are able to see atoms with these instruments. That was then also the time that those original definitions were changed. So the meter, it was still 1/10 millionth of the distance from the North Pole to the equator. But you can't just from anywhere in the Earth go and measure that quickly. It took them many years to actually do that, more than 6 years, to actually do that initial measurement of the distance from the North Pole to the equator through Paris. So you can't just do that very quickly. But now, with this definition, to resemble that meter as it was originally defined, is the length that light travels in vacuum during that interval, 1/3 millionth of a second. So now you can have a laser system, a frequency stabilized laser system, to anywhere in the world quickly realize a meter and then calibrate, say, a tape measure or something against that. So for these technologies, that was the measurement systems that was then basically developed at that time. So that resulted in 1960 in the International System of Units. Before that, until that, 1875 to 1959, it was called the metric system. And then they added a few other measurement units, and finally, or derived units as well. And finally, they arrived at the International System of Units, 1960. It was a few years before I was born, but we sang little songs at school when I went to school in about, I can't remember, it's too long ago, 1969, I think. We had little songs about the International System of Units, and a meter is so many foot and whatever, feet and whatever. So some of you will still remember that. But now let's look at Industry 4.0. So what do we actually now need for Industry 4.0? Is this current system as we basically have until Monday, you know that. The system that we have at the moment, the SI, as we know it today, will basically exist until Monday, the 20th of May, because then we implement the new one, the revised SI. But you will hear all about that today. But let's look at the technologies of Industry 4.0. This is just a photograph of harvesters on a land, and they're harvesting wheat, looks like, with a tractor driving next to it. The significance of this photograph is that these three machines can work like this. Why? Because they all have global positioning systems in them. And basically, you take it to the land where you want to harvest, and you drive onto it. It's got a GPS. You tell it how big the piece of land is, and you can program it. And the operator, it's an operator, not a driver anymore, just sits inside and he eats a sandwich and plays on his phone until the end of the line, and then you just have to turn it around again. But they then basically work like that automatically. So they move like that in unison. The next step, of course, if you can do that, is to have a driverless tractor. But we already have it in Africa. We've got driverless taxis, you know, because it doesn't stop anywhere or so on. So we assume they're driverless. But this is a driverless tractor. And it's not science fiction. They exist. And you can now wake up in the morning, grab a cup of coffee, and while you're drinking your coffee on your cell phone, tell the tractor, go to land number 2 and plow it for me. And it's not science fiction. It happens. And you have these tractors, they call it robots, basically, already, agricultural robots. The one that really caught my attention when I looked at this was this mechanical bee. As you know, we've got a big problem, and that's really a crisis internationally with bees dying out because of pesticides and other things. And one company basically said we should start to build mechanical bees. And again, this is not science fiction, this is patented. So it has already been patented by a company. And the first prototype has been made. So we may soon have swarms of mechanical bees. But I just had this picture in mind. You know, you're driving on a highway, and the next moment a swarm of bees comes past and you splat on your windscreen. What will happen if it's this swarm of mechanical bees? But let's think about this later. But it's very interesting. And think about the measurement technology that you need to make this, and then to monitor this, to make sure it doesn't land in your beer. So you need a lot of technology for this type of thing. Then we get to rapid prototyping, 3D printing, advanced manufacturing. And you know, in the old days, you basically made a die or a mold if you wanted to manufacture a component. Then you melt something like a metal or a plastic, and you pour it into that mold. You let it solidify, and there you have got your product. Most of the plastic products that we use today are still made in that way. Now, these days, what you can do, of course, you all know. You can take a powder to a 3D printing machine, and you can tell it, print this for me. You make a drawing on a CAD, and you tell it, print it for me. And these are the type of components you can now print. And this was actually done in South Africa in the biggest 3D printer in the Southern Hemisphere, as far as I know, or at least in South Africa, at Aero Swift. And they basically produce parts for aircraft, engines and things, but you can now print this type of thing. This is a photograph of a device that we're making at Nmisa with the University of the Western Cape, and this is a silicon photovoltaic cell that we're growing nanowires on. Why would you do that? Because you want to maximize the surface area that the sun actually sees, and so you can absorb more light onto your device, and by that you can increase the efficiency of your photovoltaic cell. But look at the scale there, it's 200 nanometers. 200 times 10 to the minus 9 or 2 times 10 to the minus 7 meter. That's very small, and again, you need a lot of technology to measure those type of things. So applications, we already quickly told you what we are doing in 3D printing. These were components that were printed at the Nmisa. For the device, there's something called the silicon sphere for an X-ray crystal density experiment that you will hear about later. And we just had to quickly make a holder. You don't want to hold it in your hand because it then weighs more after you've done that. So we wanted a holder that we can put it in, and it must be very stable. So we just quickly did the drawing. We put it into the computer, and Peter and his team printed these holders. That is on the macro scale. On the micro scale, we can manufacture things at nanometer scale as well. This was done in our focused ion beam scanning electron microscope at the Nmisa, that ZEISS that I showed the photograph earlier. And it can do electron beam lithography. So if you look at the scale there, you can't see it, but that N of Nmisa is basically about 2 micron from the left to the right. So it means that first left-hand leg of the N is about 200 nanometers. If you know your size of a silicon atom, that's about 0.2 nanometer. You can put 1,000 atoms in there, in that left-hand side leg of the N. And our instrument can actually do that. So we can actually tell it, put silicon atoms in that left-hand part of the N in the middle to fill up that space, one line, one atomic line. These are the type of things that we can do these days. So in the old days where you made a chip for a computer and you had a piece of silicon that you grew epitaxial layer on with organic metal vapor phase epitaxy and chemical vapor deposition and all of that, and then you had to etch it out and cut it down and whatever. Now you can actually go to your scanning electron microscope or your electron beam instrument, and you can tell it, just print or make this quickly for me at atomic level. And it's also not fiction anymore, it is happening now. So, but again, so what measurement technologies do you now need to be able to measure this world and help the development of this world? Can we still have that piece of platinum that Jennifer will tell you more about sitting in the vault in Paris, and I actually have the key for that as the president of the CIBM. But can we still have that? You know, the kids are telling me, Uncle, it's just not cool. We need something better. We need something more modern. And that is actually why we worked the last 20 years to find another way to realize mass, the kilogram that Jennifer will tell you all about. So there we have our Industry 4.0 now, with all those different measurements that we need for all that technology. So we had to then go and do something. And that is a picture of Dr. Damana on 16 November 2018 at the General Conference of Weights and Measures in Paris. South Africa in French is Afrique du Sud, so we sit first in the alphabet. And we had to, the CIPM, the International Committee of Weights and Measures, we prepared a proposal to the CGPM saying that here's the revised SI that you will hear all about later today. And they had to vote on it. The member states of the Meter Convention had to vote on it. And Dr. Damana stood up and he said, I vote for the revised SI. So he made history for Africa, another first for Africa. And he made history because he voted the first person to vote in the revised SI. It was then adopted by the CGPM for implementation in 5 days from now, 20 May 2019. So, and that is the system that we have, that you will hear a lot about today, basically with the defining constants. So we have the 7 base units defined in terms of defining constants. But my colleagues are going to tell you a lot more about that. So this is the committee that actually was elected at the same CGPM, and they then elected me in March as their president. So this is the committee that must now look after the implementation of the revised SI. So we have got the revised SI. Perhaps we just need this computer is a bit slow, a revived CIPM. So I'm not joking. We will make sure that we are more modern than the previous CIPM and that we can really implement and make sure the world knows what to do with the revised SI. And then if new technologies in the foreseeable future forces us to further revise the SI and introduce other units or measurements, that is our job. Merci beaucoup. Kia liboga. Dankie. Thank you.
Thank you, Dr. Lo. I think having last touched a science textbook, most of it went over my head. But I did get the message to say with every industrial revolution, there is a scientific measurement revolution that is required, and hence the reason for the revision of the SI. I think we'll try and take questions maybe after the next speaker to make sure that we keep to the time. Our next speaker is Dr. Jennifer Clark. She is going to be giving us a presentation on the Kibble balance. Dr. Clark is an international development specialist at the National Physical Laboratory in the UK. She has been playing a major role in the collaboration between the NPL and the National Metrology Institute of South Africa in the development of the kilowatt balance. And she'll be talking us about that development towards the revision. She has been very, very instrumental in ensuring that the revision that is happening can be well articulated. Welcome, Dr. Clark, to the stage.
Hi, everyone. I'm assuming my presentation, you're going to sort it, JJ. So I work at the National Physical Laboratory in Teddington. I arrived here on Sunday and have been very kindly hosted by our wonderful colleagues at Nmisa. There it is. So my talk is mostly going to consist of a brief history of mass and mass metrology. And then I'm going to talk to you about the revised SI and the new definition and how we're going to realize that SI going forward and the technology available to us, namely the Kibble balance. So mass metrology has been around for a long time. It originated here in Africa. Mesopotamian weights were made from hematite have been found that dated from 2300 to 2000 BC. And we found other similar artifacts from ancient Egypt in 2000 to 1700. And perhaps the most universally known mass metrology standard are the carob seeds, which I believe, or have been told by the mass metrologists in the UK, are the basis for the carat, which is the universal size of seeds that were used to compare the weight of diamonds and other precious jewels and jewelry. Very important measurement to have throughout history. So after a lot of development and each country having their own national scale, as Wynand was saying, with the British pound, the British yard, or the French roue de poids of the length of the king's foot, in 1668, John Wilkins in the UK started to draw these links between length and mass. He proposed the use of a volume of water to define a measure of mass, as Wynand said earlier. In 1799, this was picked up by the French Academy of Sciences, and they did a series of experiments to determine if A, this was true, and B, to see what exact volume and what exact masses were the best used going forward. And they determined that the mass of 1 cubic decimeter of water defined a kilogram at 4 degrees. It's pretty cold compared to here. This was then transferred to the archives and is referred to as the Kilogram des Archives. It's the first official reference prototype of the kilogram. Difficult to transport, though, when you're walking around with a big litre of water. This was then followed by, in 1875, the signing of the Convention of the Meter, as Wynand said before. And in 1883, this was decided that perhaps water wasn't the best way to have a standard unit of weight. So they moved on, and Johnson Matthey in London was commissioned to produce these platinum iridium standards, the ones that you can see just here behind me. Initially, they produced 3, and they called them the IPK, and then they produced 40 more. In 1889, the copies were distributed to all the signatures of the meter convention, and the kilogram was formally ratified at the first meeting of the CIPM. Since then, we have expanded our idea of mass from the practical scale that we can see around us every day, which is indicated by the blue arrow, to consider things that are very difficult for us to measure or here on Earth. For example, the mass of the sun. It's a bit heavy to put on a scale. But all the way down to tiny, tiny atoms, such as the mass of a hydrogen atom. Again, very difficult for me to pick up an individual hydrogen atom. And at the center of all of this is the IPK, the prototype kilogram. This is agreed all around the world. So if it's agreed all around the world, well, why do we really want to change it? Well, for starters, traceability. Everyone has to compare their copy of the kilogram to Le Grand K in Paris. Everyone has to be related back to Paris. No laboratory can have their own measurement of the kilogram. This is what our journey, every time we wanted to calibrate our kilogram, looked like. We had to take it from London, and we had to go and introduce it to its fellow kilogram over in Paris. And this led to a very long traceability chain, starting in the IPK, Le Grand K, over in Paris at the BIPM. They then had a set of working standards at the BIPM, which could then calibrate your national prototype, which could then calibrate your secondary standards at your NMI, which could then calibrate your laboratory standards at your accredited labs, and then your working standards at the end users. But at the end of the day, every single one had to be traceable back to Paris and Le Grand K. A second problem is stability. We assume that those platinum iridium blocks don't change. They're always a kilogram. They always have been, and they always will be. But the copies, when they compared them to the kilogram, seem to not weigh the same amount, as indicated by this graph. This line here is 0. This is the Le Grand K, indicated by this thing, our fantastic, not changing platinum iridium artifact. And all of these lines here are the copies that were distributed and made at the same time. So why are they so different? Well, one hypothesis is that perhaps these are actually the stable weights, so we should shift the whole graph, and the IPK has been losing mass. But another theory is that, well, perhaps actually all of them are gaining weight by mass and mercury accretion. So we shift the graph the other way. And it's exactly this. We don't know what is going on. We don't know if the Le Grand K is stable. We don't know if the copies are stable. Nobody knows. And we need to know. Mass has underpinned our society for such a long time now. We need to have these measurements to be able to move forward for the Industrial Revolution, as Vinand was saying. So the solution is the revision of the SI. So some of these were redefined a long time ago to get rid of their artifacts. The kilogram was the last artifact that was left, the lone wolf. With the new definition, we are removing our dependence on this single artifact left in Paris, and we're relating it back to a fundamental constant of nature, the Planck constant, or H. So this is the new official definition. It was ratified last year in November. South Africa casting the first vote, very important, very impressive. And 5 days from now, this will be the definition, and Le Grand K will be relegated even further into the archives. And yeah. This means that after this date, we need a new way to realize the kilogram, and we need to have methods that everyone agrees on. Now, if everybody can realize the mass in their own way, we need to sort of have consistency. We need our methods to be comparable, and we need to have a significant number of measurements to test that they're all comparable. You can't really compare two measurements on their own because you'll always get a straight line and you'll always be able to say they're comparable. So what happens to the traceability on Monday? Well, this is what we have today. So we have the IPK, the national standards, and the end user primary standard. And this is what will happen on Monday. Everybody will be able to, every NMI, theoretically, will be able to have a primary realization in their own lab that they can then calibrate their national primary standards and their national secondary standards. This isn't the complete end for the platinum iridium kilogram because you can use the primary realization to calibrate a group of artifacts such as the platinum iridium if you so choose. Now, one interesting thing about this diagram is you might have noticed that the uncertainties quoted at the end of these trails are different. And in fact, the new traceability chain has a higher uncertainty. That makes you question, why would we do this? This is increasing the uncertainty. This is exactly what we don't want to do. But in fact, we assume, the reason that this side is so much lower is because we assume that the IPK has no uncertainty. It is a perfect kilogram. But we know that's not true. So in fact, this could be 10 times as big, 20 times as big, or it could be 10 times smaller or 20 times smaller. But never mind. At least on this side, we actually know what the uncertainties will be. We can characterize them, and with the new methods, we can actually give an accurate uncertainty to our end users. This is very important when we're talking about Industry 4.0. People need to know what they're measuring to be able to develop their technologies further. So what are these primary realizations? Well, there are two main methods that have come to the fore, the Avogadro sphere and the Kibble balance. Both contributed to the definition of the Planck constant, as you can see in this lovely graph here, with the green, sorry it's so blurry, I took it from a paper. These green points are the Kibble balance measurements, and the brown points are the Avogadro sphere measurements. Now, the two most important measurements, for me anyway, are this measurement here, which is the MPL Kibble balance, and this measurement here, which is labeled NRC, but you'll find out more about why I like that measurement later. So how do they work? Well, the Avogadro sphere is a 96.3 millimeter diameter sphere of pure silicon crystal right here. It's very shiny. And what you do, we use the Avogadro sphere to derive the Planck constant from Avogadro's number, or vice versa, you can use it to determine the kilogram. And to be able to do this, essentially, the sphere is intensively measured. We determine the roundness of the sphere to make sure that it's consistent on all sides. We determine the isotopic composition to make sure that it's made up completely of silicon-28, because otherwise the mass would change. We look at the lattice spacing to make sure that they're evenly distributed. And we use the surface chemistry to determine if there is any silicon oxides forming on the outside and contamination. Now, this is a good experiment. This is an interesting way of realizing the kilogram, and it's very different. However, it doesn't really seem the best way forward, or at least not to us at MPL, especially when we have something called the Kibble balance, happily invented at MPL in 1975 by Brian Kibble. The reason that we think this is best is because all the principal qualities allow that you have to measure in order to realize the kilogram can be measured with very low uncertainties, which contributes to an overall low uncertainty in the kilogram. So it's essentially a two-part experiment which relates virtual mechanical power to virtual electrical power. This probably doesn't mean very much. So how does it work? Well, essentially, we have a seesaw. We balance electrical and mechanical power. Here, we have our electrical power, where B is your magnetic field strength, I is your current, and L is your length. And in here, we have an electromagnet. This is used to balance our mechanical power, our weight. And this is where you would put your platinum iridium or any weight that you wanted to measure. However, the problem with this is the magnetic field strength and the coil length are actually quite difficult to measure accurately. So Brian Kibble came up with a solution. We used the two-part experiment. So the first part is exactly like a seesaw. We balance out the two sides. We balance the electrical power and the mechanical power. But then we do a moving experiment. We move the electromagnet up and down through a magnetic field at a constant velocity to generate a voltage. Like this. And this generates this equation here. This also means that we don't have to know the coil length as accurately, and we don't have to know the field strength as accurately, which means that our overall measurement can be much more accurate because we've determined it through the voltage. So what does it actually look like? Well, the very first balance was massive, and it worked in air. There isn't much for scale here, but this is a pallet truck about this big, from there to there. It's quite large. At the time, it produced the lowest uncertainty result that contributed to the fixing of the value of the Josephson constant, adopted in 1990. But before the balance could see that, we decided to take it all apart. And the reason for that is because we had a better idea of how to do it. And the Mark II Kibble balance was created. This time, we didn't work in air. We worked in vacuum, hence this lovely casing around the outside. And this balance was purely designed with the aim of measuring the Planck constant to ultimately allow for the redefinition of the kilogram according to the fundamental constant of nature. It ultimately achieved an uncertainty of 200 times 10 to the minus 9 of the Planck constant while it was at MPL. We then gave it to Canada, and Canada has actually produced the lowest uncertainty measurement of the Planck constant. So that little tiny spot that I showed you a few slides ago where it had a tiny uncertainty from the Kibble balance, that's with an MPL piece of equipment. Okay, it was done by Canada, but still, we're going to claim a little bit of credit for that. So if Canada have the Mark II balance, well, what have MPL been doing? We came up with a new idea, the next generation of Kibble balance. We wanted to develop a Kibble balance which was simpler to build and easier to operate, and therefore more accessible to more NMIs. The more data points you have, the better the measurement, the better the understanding. And this is being produced with other NMIs, including NMISA. And it's really aimed at realizing the mass scale at the SI level routinely, so not just on a one-off. The old balance, the Mark II, takes 3 or 4 days just to sort of stabilize, and it's the size of this room. It's massive. This one, it's a little bit smaller. I could probably fit it on this desk here. Admittedly, it has some systems around the side, like electronics and computers and stuff, but it's much more portable. It has we're designing it with the robust electronics, and we want to make it easy as possible to use. But what you might notice is it doesn't seem to have a seesaw. So how does it work? Does it use the same principles? Well, here's how it works. We have 3 phases. In the first phase, we put a current in the electromagnet coil at the top, and this interacts with a magnetic field. This then balances the gravitational force on the empty carriage in the middle that you saw. This is essentially the tear. Oops, sorry. And it means that we don't have to have this balance. Normally when you tear a balance, you just make sure that there's nothing on either side and that it's pretty empty and it sort of is flat. This is essentially that. This is essentially that. The next thing we do is we add a mass, this little ball in the middle, and the carriage instantly goes down. The same as on a scale when someone sits on the side of a seesaw. It goes down. And the next part is where we measure that. So we put a current in the lower coil, which interacts with a magnetic field, and this balances the gravitational force on the mass. And it goes back up to the balance point. The third part, phase 3, is where we, again, put a current in the upper coil, which interacts with the magnetic field, and this drives the carriage up and down. So this is the same as that moving part that we talked about earlier in the seesaw balance. This generates, this lower coil here, then passes through a magnetic field and generates a voltage. And this voltage allows the calibration of the kibble balance. So essentially, we've taken something that had horizontal, sideways motion, up and down, and we've made it like this, and it goes up and down like this. That means everyone loves that. It's the best part of my presentation. So where have we got to so far in this development? If you've noticed, all of the pictures I've shown so far have been 3D pictures done on a computer. Well, the first thing that we decided to do when developing this was build a technology demonstrator, or TD1. This was just to prove to ourselves that our principles were correct. It provided initial designs for the interferometer, the magnet, and the coil that were ultimately going to be used, and it's been used as a testbed for developing and updating and improving the electronic software and the original balance. It's still significantly smaller than that Mark II balance. It could definitely fit in this space over here. We took that, and this is what it looks like. It still works under vacuum, and it still has the seesaw design. So when you come to visit us, this is what it looks like most of the time. It's very, boring and uninteresting. Next stage was to realize our vertical balance. And this was happening in technology demonstrator number 2. It looks like something out of War of the Worlds. It's fantastic. So we've built this, and we're now testing it. And this will allow us to evaluate the flexure strips in the middle, these sections here, which help the carriage move up and down. And just to double check that our initial tear, where the carriage is empty, works correctly, and as we think it does. And we're hoping that we'll have completion of this testing completed by the end of 2019. This one is the instrument demonstrator. We built this as a practice run, a dry run of our final design. They are this big, and I believe that people have seen them. They demonstrated them at the CIPM meeting in November. They were on the table. It works. You can measure a mass with it. Not quite as accurately as we'd like yet. It currently operates at 1 in 10 to the 4. But the fact that it even works is amazing. We've taken this conventional seesaw and made it vertical and proved that it works in a portable system. However, we're not quite satisfied with that. We want to keep developing it. And we already have improvements to the flexures and control system in the smaller versions, and we hope to improve the performance. In this particular one here, these initial instrument demonstrators, the mechanical construction has limited the best possible uncertainty that we can get to 1 in 10 to the 6. So what's the future? What's after this? Well, these instrument demonstrators are very good. They're portable, they're usable, and although the accuracy isn't great, it means that we can encourage other organizations to realize the SI in a traceable way. The ultimate aim for us is for it to be easier for laboratories to realize the SI on their own and maintain the mass scale at a global level rather than everyone having to relate back to the BIPM and the Legrand K. The design also means it's easier for us to measure smaller masses. So rather than having to measure a kilogram each time, you can measure 100 grams or 500 grams. This potentially means we could produce different kibble balances, ones that could work at room temperature and be used on the shop floor and support our industrial development partners. They could be used for research and development and production where dynamic weighing is important. And the other option is we could go even smaller and not just measure macroscopically, but measure microscopically. And these kibble balances could be used for pharmaceuticals. Drug discovery is very important, and the idea is that we can have drugs tailored to ourselves, where you measure tiny, tiny amounts of drugs in different mixtures for every single person. And if people could do that in a traceable way, it would make it safer over longer timescales. So how do we do that? Well, one of the options that we've thought about is a micro kibble balance, working on the same electromagnetic principles as the one we saw before. This is good. It's okay. It's a little cone about this big. It's not too bad. Well, we had another idea. Let's put it on a chip. Everyone loves things on a chip. Your phone is full of chips. So we came up with the idea for an electrostatic kibble balance. This is as far as we got with this one. We're still working on it, and it's something that we hope to develop. But ultimately, we want to develop it for industry and make it so that everyone can realize the SI in a traceable way to improve all our measurements and improve technology developments. So to sum up, mass metrology has been around for years, and it originated in Africa. The SI unit of mass itself is 130 years old, but the new definition will last even longer than that. It will guarantee longer-term stability and will allow everybody to realize the unit without having to have a lovely trip to Paris each time. However, there is a downside. The current Avogadro and kibble balances are big, expensive, take a long time to use every day. So we need a new way of doing it, and that's what MPL's been working on. And we hope that the simplification of these approaches will allow a widespread adoption of these techniques at SMI level, but ultimately in industry. The next generation kibble balance allows routine realization of the SI unit at a level of around 2 in 10 to the 8, we think at the moment, hopefully better. The design is scalable, and that's the really important bit about this. You aren't stuck at a kilogram or 100 grams or 500 grams. You could go to the micro scale or the macro scale, and that makes it industry relevant and really important as we go through this industry 4.0. So the last thing that I wanted to show you was this nice trailer for the last artifact video. Now, it worked earlier, and I apologize if it doesn't work now.
I feel like our job is to define objective reality.
It's not showing on your screens, but it is showing on this one. It's very fun, I'm going to tell you right now. It looks good on my screen. Oh yeah, that one.
We're trying to get rid of the kilogram. Mass is still tied to a single artifact in the world. A hunk of metal in Paris.
Anything that you weigh from an apple in a grocery store to yourself on a bathroom scale to drugs at a pharmacy eventually goes back to this prototype. There's a lot of things to do. It's not enough to work day and night.
Different labs around the world want to find some scientific insight that the others haven't found.
We have only 2-3 months to consider new results. There's a lot of pressure.
I really like that video because I think it really sums up the fact that it is the last artifact. It's this ancient thing, and we're getting rid of it. And I hope that Vinand, when we do get rid of it on Monday, you're going to do that badass walk down some trees with the key.
Yeah, they're giving it to me now.
Yeah. Sit on your coffee table, right?
Exactly.
And that's the end of my talk.
Thanks, Dr. Clark. I'm very impressed with myself and the speakers in the time we've kept, being that as metrologists we're the custodians of time. I hope the other presenters have taken note. But what I was really expecting from your talk was that next week, Monday, I'm going to weigh 2 kilograms lighter because of your redefinition. And maybe we should get an explanation to why that is not the case. We've got some time for a few questions. I don't know if you guys are still mic'd for the room sound. If there are any questions from the audience.
Thank you for the talk. I'm not sure if I pick it up on the presentation. I'm just thinking about it at the end. What is the effect of G, the small g, on the measurement that will be performed at different places? Because I think somehow we have slightly different G's that we measure as we go around the world. It's not always the same. Thank you.
Yeah, G does have an effect, so it is important that you measure it, but you don't have to measure it every day. G is relatively constant over a set time period, so as long as you have a measurement of G, wherever you're using the kibble balance, you could still use the kibble balance for your routine measurement of the SI. The key thing is that you have an understanding of what the uncertainty is on your G measurement. So there are gravimeters around the world, and I think a lot of the geological companies take gravimetry measurements when they go around the world. So you should be able to get access to that. And I believe that Nmisa are in the process of buying a gravimeter.
Yes, there are three things that you really need to measure very accurately. And Jennifer already mentioned voltage and resistance as well. And the other thing is
Gravity.
the G. Gravimeter. What is writing this?
Yeah, gravity. Gravity is very important.
So Nmisa have ordered a new gravimeter, and I think it arrives in about 3, 4, 5 months. There's Aletta, she knows exactly. Let me give to her to give the final answer on this one.
Team effort.
The boxes are currently in our labs.
Yay!
Good. So that will hopefully be operational in 2, 3 months from now. And then we will be able to very accurately measure gravity at the exact spot where you are going to do your kibble balance measurements.
Just a follow-up, I was asking in terms of like now the influence on the, I believe at the end there will be a comparison on these measurements.
Yeah, so the gentleman asked about the intercomparisons of the different experiments. So the idea is that once we have built these kibble balances with our collaborators, we can then use the kibble balances in situ with our collaborators. We'll each have their own kibble balance, and we can compare the results and make sure they all work. And we'll also be able to compare with the NRC in Canada, NIST, and with the organisations that are using the Avogadro sphere to really make sure that our new definition is robust and that everyone is measuring everything consistently.
Yeah, I can just quickly add to that, and Aletta can again answer this probably, but will come in. But the point is, at the moment, there are probably 4, 5 working kibble balances in the world. At the moment, what we did now was to take an average of all those measurements, and we said, okay, fine. We define the value of the Planck constant, and now we work in reverse. So, and now we determine the mass of your mass piece very accurately, but it is still on that average value. So you don't, at the moment, then use your kibble balance in your laboratory to actually determine the Planck constant there and then do the mass measurement. You use that consensus value for the Planck constant, the defining constant. Once there are more balances around, we will then start to do comparison of those measurements. The same as we do at the moment for the realization of the meter with our frequency stabilized lasers. So we compare how well can we realize and how we compare, and that we will do in future then for the kibble balances. Aletta, if you want to add? They will switch over.
It's working now, yes.
Yesterday the decision was that the first key comparison for mass.
Yeah, I think we had that one yesterday on Monday as well, and we did that.
It seems.
Yeah. try this one.
Yesterday, oh sorry, the decision was made at the CC meeting that the first key comparison will end in March next year. People must submit their results. So the first key comparison for kibble balances is happening.
There you go. Straight from Paris.
Dr. Henry? Is the mic not working?
Thank you very much, Dr. Clark, for the nice presentation.
Henry, take
Give
that
it
one.
a minute.
We need some
Yeah, never mind
innovation and
keyboard.
technology.
Never mind kibble balances.
I think, thank you, General. I think it needs some calibration. Yes, thank you very much for the nice presentation. I just want to ask one question. The impact of this, especially the kilogram revision on the school syllabus. I'm sure from Monday there will be a lot of questions being asked. What are we doing with on the school syllabus? So maybe you can share some of your maybe activities at NBL that you are doing to really help demystify this. Thank you.
Sure.
There's a mic back.
To bring you that mic.
Yeah.
So,
I'll answer it in a minute. Or I can shout. That's also, I have a very loud voice.
me too, so
Yeah.
we can do it.
Thank you. It's not working now. I'm just going to shout. So essentially, MPL has been involved in a lot of outreach activities. Didn't deafen you all. We've been, well, as of yesterday, our copy of the kilogram is actually going on tour around the UK to be able to introduce people to the last artifact and kind of explain to them what changes are happening. We also have lots of fun activities that we take in regularly into career school fairs and into demonstration lectures. For example, we have a game called the Dolls of Confusion, where we have different sized wooden blocks that are all weigh different amounts, and you have to put them in order of weight. And nobody can get it right. I've taken it to calibration labs, I've taken it to the government, and everyone thinks that they can do it, and they really can't. And it really helps emphasize the fact that you can't just look at something and know how much it weighs. You have to be able to actually have a measurement system that works. So we're doing all this outreach, going into schools and talking to them about these different methods of weighing. We're talking to our government and trying to explain to our civil servants about that. But we're also engaging with our science museum in London. And we're hosting a whole evening dedicated to measurement, where we're going to have lots of activities for the general public to get involved in, and hopefully generate a lot of interest outside of the NMI community around the importance of measurement and the excitement around the redefinition of the kilogram. The other thing that we do at MPL is we run training courses that industry can access, which means that they can get trained on the importance of metrology and on the redefinition. And we feel that this really helps with the engagement going forward. As for the actual school syllabuses, I'm not sure, I haven't seen them. I know that I learnt about uncertainty and about the kilogram when I was at school a few years ago. But nowadays, I'm not entirely sure.
Yeah, I can add two things to that. In the first place, from the CIPM, at the moment, the SI brochure is version 8, edition 8. And that still has the old definitions in it, like the kilogram is the weight or the mass of the IPK in Paris. The new edition is the 9th edition, and the CIPM and the CCU, the Consultative Committee for Units, and then the CIPM worked very hard the last 2 years to get that finished. I actually received a copy from the director of the BIPM 2 days ago, on Monday. I received the first official final copy of the 9th edition of the SI brochure. It will go live probably today or tomorrow on the BIPM website. And of course, it must be published before Monday, the 20th of May. So then you will have the new SI brochure explaining or giving the new definitions in terms of the defining constants and a few other updates on the derived and other units. In South Africa, what we are doing is that we're on the route of partnering with the Measure program at University of Cape Town, the They will also be here from later this afternoon and will give presentations on it tomorrow to develop curriculums for university students and for schools. So there's a whole program now running between Nmisa and UCT to develop that. And it will firstly be introduced into the university curriculums and then into schools. So we will then have a new curriculum that we will explain to school children what the new definitions are and how it works. So anyone that's interested in that, there are actually talks tomorrow afternoon with Tim Pryor from the NPL, and some of the UCT people are here, will be here, and there will be talks about that tomorrow. Thank you.
There was a hand at the back there.
So tied with the fourth industrial revolution is the move to the extremes of the scales in terms of mass. I think you showed one of your slides showed from the very small to the very big.
Yep.
Tied to the fourth industrial revolution is the move to the very small. So the redefinition of the kilogram, does it have any significant implications, especially as it applies to the fourth industrial revolution at a smaller scale? That's the question.
You want to give it a go?
I'll give it a go.
Okay.
I think I have an answer. So I don't think the actual changing of the definition has a significant impact, apart from that you're not tied to a kilogram, which means that when you're going down the traceability chain, you don't have to say, okay, well, there's a kilogram there and the uncertainty was 1, which means that when I go 10 times smaller, my uncertainty is 10 times bigger. What it means is that you could traceably realize a smaller mass immediately. So your uncertainty would just be from your actual realization, not from that comparison to the larger mass, which would ultimately mean that you'd get longer, more accurate measurements directly. And that's one of the reasons that we want to try and develop these micro and macro kibble balances, because they would enable people to measure a microgram immediately without having to measure a kilogram, then measure a microgram weight and say, okay, well, the weight is this much more imprecise than that weight. And that will hopefully lead to, as I was saying in my presentation, more accurate weights that could be used in the pharmaceutical industry or in additive manufacturing. For example, when you're making composites, you want to really accurately know what chemicals you're putting into your composites and the weight of them. And by realizing mass directly with these dynamic measurements through the micro kibble balance, you'll have a lower uncertainty, so more accurate measurements. Does that answer your question? Yeah.
Yeah, it also has a very interesting effect at the atomic mass unit level. But I'm not going to really talk about that now. I think Dr. Gorst Alman is talking about the mole later, and will probably say something about that. But just because of the new definition and the way that the uncertainties change, is a very interesting effect at the atomic level. But okay, we will hear about that later.
Thank you. Just to follow up on that question on the curriculum, in the South African context, it's not more about the curriculum per se, but also the delivery of the curriculum. So what is the strategy developing the teacher in order to ensure that when they deliver the curriculum to the learners better understand it? Because quite fun that you develop the curriculum, but those who are delivering that don't understand that from the first instance. Do you have sort of a trainer program that is in mind to assist the Department of Basic Education? That's point number 1. And then on the lighter note, please check the petrol and diesel that is accrued. It's very expensive.
Yeah, we've got a few jokes about that, but I'm not allowed to tell it. I'm actually going to give to our CEO to answer that question.
Thank you, Bernard. I think that's a very important question that talks to, are we able to get this new way of doing things understood by the people we are trying to train, so that in future they can be able to move into the innovation space that we want the whole of Africa move into. As South Africa, what we are doing currently is, as Bernard indicated, we partnered with UCT, but not the Department of Physics only, with the Department of Education as well. And we are bringing in the Department of Education, the National Department of Education, into that program, so that as we develop the curriculum, we would be simultaneously working on the transmission mode, how we're going to deliver this to learners, nowadays they're called learners, not students anymore, to the learners at the end of the day. So we are considering those aspects that you've raised. We're hoping that when this comes into effect, we would have a good, seamless transition that takes into account the teachers, the learners, the environment that we are operating in, and everything else around it. And I think when the measure program does their presentation, you will realize that we also try to make it playful. We've got measurements that will be launched during their presentation, and I think you will be able to see that we're trying to make it more inclusive as opposed to elitist as some of these things have been in the past.
Yeah, I can just quickly add as well, you were not here on Monday with the Industry 4.0. We're also throwing in the technology because we are using virtual reality. And what we have developed are a few virtual reality training courses that you can do on your computer. And the latest one that we are doing now is a virtual keyboard balance, and that you would be able to load it onto your computer and then do the full experiment. That whole experiment that Jennifer showed, you will be able to do that on your computer. It won't be as pretty as this one, but it will be fine. You know, it will be interesting. So the kids will be able to play with it, and I think they will find it really interesting, and that will really help, we think, for them to understand it.
Thank you, colleagues. I think we've covered really the topic. We've come to the end of our first session. We just have a few announcements to make around the final session. We do have some of the balances sitting outside for those who want to see. Some of them have been 3D printed and looking all nice and lovely. They're probably somewhere outside at the distribution boxes. Before we go to tea, we have been asked if we can take a group photograph, which will be at the back entrance of the hotel by the fountains. I think there's fountains there. The next item is that the presenters for the next session should load their presentations before the end of the tea break. So during the tea break, if they could just load their presentations. The first movement from now, if you can all move to the back of the hotel entrance for the group photo. Thank you.
what's happening.
Good morning. My name is Ndwakuru Mukupi. I am the CEO of the National Meteorology Institute of South Africa. We are currently running a conference at the mainland Main that is focusing on the revised SI. As you know, I know most of you would not have heard, but the International System of Units as we know it is currently being revised. There was an agreement that was made by the CGPM, the General Conference on Weight and Measures in Paris last year on November 18th, that focused on specifically revising 4 of the 7 base units of the International System of Units. This revision was agreed to through a voting that we as South Africa participated. We contributed to that decision that was made. And the agreement was that that revision would come into effect next Monday, the 20th of May, which coincides with World Meteorology Day, which marks the signature or the signing of the Meter Convention in 1875. And with that in mind, we decided to run this conference during this week that looks at the impact to the science world of this revision. It also looks at the impact to the layman in the street as to whether there are going to be any changes that you as the people in the countries would be able to feel when this change happens. The important thing to note is that we've worked very hard as scientists to make sure that when this revision, there will not be any noticeable impact on the person in the street. There would not be any noticeable change because we have made sure that there will be a seamless move. There might be a slight move with the revision of the ampere. As you know, it's the kilogram, which is known to be the last standing artifact. There is the ampere, the mole, and the Kelvin that is going to be revised. It's only in the ampere that there might be a step change that happens. But as I indicated, the scientists have made sure that you will not feel the difference as the consumer and the end user at the end of the day. In the conference that is running throughout the week, we started it on Monday with a focus on the 4th Industrial Revolution. As you know, during any industrial revolution, there is a need for a change in the measurement system, and hence the change in the revision that we are talking about now. From yesterday up to Friday, we'll be focusing specifically on the revision of the SI, from the impact to science to how we're going to teach it at school, as the curriculum at school would have to change on how we teach the measuring system in the world. So we are excited as scientists. This is a very exciting moment. We hope you also share in with the excitement that we're having, and do understand that we are here to make sure that there is no impact as such for you. But the biggest thing being, we try to make you understand what we do so that those innovators out there can be able to use this system to put into their innovations and ensure that we become competitive as a country, and not just as a country, but as a continent as a whole. Thank you very much.